Hi, today we're looking at section 3.4, solving exponential and log equations. We spent the last two periods discussing and reviewing the properties of logs and of exponential rules. So now we're going to use those properties in the context of solving equations. So a couple of properties I want to just refresh your memory about are the one-to-one properties, which says because that equal sign is there, then this side of the equal sign has to be exactly the same as that side of the equal sign. So that's the property of equality. So if this base is the exact same thing as this base, the only way that statement can be true is if this exponent equals this exponent. And same thing is true for logs. If this log base A is the same as this log base A, then to make that equal sign in the middle be true, x has to also equal y. The inverse property, we talked about this. So if I take base A, because that's the base of my exponent, I make it the base of my log, and the argument would be x, and then that would be equal to log base A of x. And then we have it in the log form where you have log base A, and then the base of the exponent is the same. So if we rewrite that, we get a to the x equals a to the x. Okay. Remember when I say solve something analytically, that means to show the algebra steps necessary to isolate the variable such that you end up with a statement x equals all the other stuff that you solve for, and then that's what you enter into your calculator. So I expect to see on your paper getting to this, and then you'll put this in your calculator. Exact answers should always be left when possible. So you're going to have to understand that when you're working a problem, if some part of it gives you an exact answer, that part may be exact, where the other part may need the calculator to do it. So exact answers will always be required first. So if you just randomly start punching stuff in and put all kinds of approximated answers down, you're very well going to not do well because some of those that are exact would be considered wrong. Rounding answers to 3 decimal places unless the problem says something different. So for instance, if it's a money problem, you wouldn't go to 3 decimal places, because who walks up to the cash register and pay, and the cash register says, I want $10 and 0.3476 cents, right? So make sure it makes sense to the problem. Application problems must include the unit as part of the answer, and you will not receive credit for the answer without that unit. So just pay special attention to that. All right, so problem 1a, we're solving the exponential equation. We have exponential base e on this side and exponential base e on this side and exponential base e on that side. And so if this base equals this base with the property of equality, then this has to equal this. So I can pull those exponents off, equate them using that one-to-one property. Remember, this is just for your reference as you're looking through the notes on paper. You don't have to state what or why you did what you did. You just have to be good at showing your steps, doing your steps in order, making your steps go down vertically, and making sure the last thing I see in your work is your answer. All right, so to solve this quadratic, we're going to move that x squared over because we want to try and factor, and we're always going to try and factor when the a value is positive. And so are there factors of 4 that will subtract to give me -3? Absolutely, so it factors. Then according to the zero product property, we set each factor equal to 0, and we know what our x's are, and then we check. So remember, we're checking to see that this exponent equals this. So I put the 4 in here. 4 squared is 16. When I put the 4 in here, that's -12 and -4, so -16 here, -16 here. That checks. And then I do it again with the -1. So -1 squared is +1, so that makes that -1. -1 times -3 is going to be, excuse me, is going to be +3, and then -1 gives me that -1, so that checks. And so then I can say my solutions are x equals 4 and x equals -1. If either one of these did not check out, then it would not be included as part of your solution. Okay, so 1b. So we have 3 times 2 to the x equals 42. So remember your PEMDAS, parentheses, exponents, multiply and divide. So you can't do this multiplication and say 2 times 3 is 6. We can't do that. That's a no-no. So we need to get this by itself. So first, I'm going to divide both sides by 3, and that gives me 2 to the x equals 4. And then to get the x, the variable that's in the exponent, down into the problem, I need to convert it to a log. So the base of the exponent is 2, so the base of the log is 2, the argument is 14, and the output to any log is a power. So now I have x isolated, so I can go into my calculator and work that out. So what I did here is I used the template that we talked about last class. So alpha window, choice 5, and I typed it in just like it looked, and it gave me my answer. And then I did it as if I don't want to mess with the template, and I just used the change of base formula, which is log base 14 divided by log base 2, and you can see you get the same answer. And actually, when your calculator does this right here, it's actually making this calculation. Okay, so when you write your answer, it's an approximation, so we're going to use approximately to 3 decimal places, which is going to be 3.807. And we can easily check that out on a calculator because we would have the calculator. All right, problem 2C. So it's an exponential problem. So I need to isolate this exponent so that, in this power term right here, so I can get up to the exponent. So I'm going to move the 5 to the other side. So I have e to the x equals 55. How do I get the variable out of the exponent? I turn it into a log, and I use ln log because the base is e. So ln of 55 is x. So I use my calculator, punch the ln button, and I get 4.007. So when I check that out, that also works. All right, for number 1D, we have a variable in the exponent. It's all the way inside here, so I need to isolate this term to make that happen. So the first thing I'm going to do is move the 4 to the other side, and that gives me 15. And then I'm going to divide both sides by 2 to get the power by itself. And now that I have the power by itself, I can convert it to a log so I can get that t out of the exponent and down in the problem to be able to solve it. So the base of my log is 3. The base of my exponent is 3, so the base of my log is 3. The argument is 15 halves equals, and then I have 2t minus 5. All of this is the exponent, so all of this is what the log equals. So then I need to get t by itself. So I'm going to move the 5 over, and then I'm going to divide by 2, and I get my statement where t is by itself. At this point, then I'm going to go to my calculator to figure it out. And I would highly recommend using the templates on your calculator. Make the fraction look like a fraction. Make the base look like a base of the log. If you make it look like the problem is on your paper, you are less likely to miss it because you enter something incorrect. So you can see I have log base 3 of the fraction plus 5 over 2. I made it look exactly like it does on my paper, so there's no room for error there. And I get 3.417 and some more stuff, and I'm going to 3 decimal places, so I'm rounding right there to the 7. The 5th digit is 0, so it's not going to change the 7. So my answer is approximately 3.417. So on problem set 2, we're going to solve everything analytically. And remember, if you'd like to stop the video before you see my solution and see how you do, you can always do that. But analytically, again, means get that x all by itself on one side and then go to the calculator if you need to. So in this case, the base of the natural log is e. So to get the variable out of the argument, I have to convert it to an exponent. So I would do base e to the power of 2 equals x. And that's what my exponent is going to look like. And that's just a number, right? E is a letter that represents a number, so that number squared gives me approximately 7.389. And in case you have forgotten how to do that, that is second natural log, and you get your e to whatever, and then you can just put in your 2, and you get your numeric answer that you can round. So there's a 0 after the 9 right here. So the 9's not going to round up, and it's just approximately 7.389. All right, so now we have a natural log with the variable inside the argument, which is inside a square root. So we've got to dig all the way down to that x and get it by itself before we go to the calculator. So there's nothing that I need to move over or multiply or divide by. So to get out of the argument, I'm going to change it to an exponent. So the base of the natural log is e to the power of 5 equals the argument. So it's going to look like that when I change it to exponential. How do I get down to the x there? I got to get rid of the square root. So in this case, I'm going to square both sides. And so that on this side, a power to a power means I'm multiplying. So I get e to the 10th, and then I will have x minus 8 over here. And then we're going to isolate x. So we're going to move the 8 over to the other side. And we have this statement. And remember, e is just a number, so that's a number plus a number. So when I go to my calculator, I do second natural log, and the power is 10, and then I say plus 8. And so I get, let's get that out of the glare so you can see that better. There we go, up there. And then I hit enter, and that tells me approximately what it is to 3 decimal places. Notice there's a 7 after the 5, so that's going to round my 6 up, and I'm going to find that it's approximately 22,034 and 466 with the point there. And I guess I could read that properly if I was paying attention to what I just said, but 22,034 and 466 tenths, hundredths, thousandths with the DH there at the end. All right, great. Let's move on to the next one. So here we're all in natural, or not natural log, log base 6. So we've got log base 6 here, log base 6 here, log base 6 here. There's more than one log over here, so I can't use my one-to-one proper directly. But since they are the same base, I can use my condensing rules to bring this down to a single log. So when it's connected with subtraction, then we can condense it back down with division. So it's this argument divided by this argument, one word log base 6. Now we have a one-to-one situation because we have log base 6 here, log base 6 here. So that means this argument has to be equal to that argument. So we can pull that out. And now we need to get these two x's together. So I need to kind of get figure out how I'm going to get those x's together. So I'm going to start by multiplying both sides by 5 and get rid of the fraction on this side so I can just move my terms around to get them together. And then I'm going to move my 3 over here with my 10, so that gives me a 7x equals to 14. Now I divide both sides by 7 and I get 14. And so when I check this, I'm checking to see that this argument and this argument make a statement that works out true. So if you're using your calculator, or it's part where you could use your calculator, you can just punch it in. Or we can say 3 times 2 is 6, 6 plus 14, and then if I divide that by 5, will I get 12? Oh, I'm sorry, 4, 2 times 2. So it does check out. Problem D, we have 5 plus 2 natural log of x equals 4. The variable is in the argument, so that means I need to get this log by itself so that I can convert it to an exponent and get that x out of the argument and be able to solve it. So the first thing I'm going to do is subtract 5 and move that over. And then I'm going to divide both sides by 1, so I get the natural log equals 1/2. And now that the log term is isolated, I'm going to convert to an exponent. So the base of my natural log is e raised to the exponent equals x. And so I know that this is the same thing as 1 over e to the 1/2. So I would probably put it in my calculator like that. Excuse me, just so that I kind of have everything in the right place, because we know we don't leave negative exponents. So when I do that, I use all my templates and I get the fraction template. I put 1 over, and you could use the exponent here to be 0.5, or you could do 1/2. I always encourage students to make it look just like it looks like on the paper so that you don't accidentally have any flub ups or anything. So this is what I got when I entered it in the calculator. There is a 5 after the 6, so rounding to 3 decimal places, that's going to be approximately 0.607. And so remember, you're using your approximations, and since it was a calculator problem, I just plugged it back in here to make sure this side equaled 4, and it did. All right, and working on our last problem, number 3. Part A says we have $500 at 6.75%, and it's compounded continuously. How long will it take to double the amount? So there is a lot of information here, so pay attention to your principal amount. Here is your percent, but we always change the percent to a decimal, so we move it twice back this way, so it's 0.0675. Compounded continuously means which formula are we using, the compound formula or the continuous formula, and we're going to use the continuous. And then we want to know how long is it going to take to double. So how long does it take 500 to become 1,000 to double? Okay, so using the PERT, the continuously compounding, and 1,000 is the amount I want to end with. That's what I want it to be when it doubles. It starts out at 500. We take e to the rate, which is 0.065 t. So to get to the t, I need to get the exponent by itself. So I'm going to divide both sides by 500, so that is 2. Then I'm going to convert it to a log, so the base of the exponent means we're doing a natural log base e of 2 equals the power, which is, remember, the output to a log, and then we can divide both sides by 0.065. So when we put that in our calculator, we have that, and so our answer is 10.2688 and some stuff. So I go to 4 places, which is 8, which makes the 8 turn to a 9. And so I'm going to write, since it's an application problem, this is what I got on my calculator. And to answer the problem, this is not answering the question because this doesn't have any units and it's not to 3 decimal places. So we're going to go and say the answer is about, because we are approximating 10.269, and years is the unit of time we're talking about. So this would be what I would want to see as your answer. All right, so this is the last problem here. The yield in V is in millions of cubic feet per acre for a forest at age T years is given by this equation. Graph the function on the calculator. So when I put it on the calculator, I put the function in Y1, and I set my window to be this, and it's just a rough sketch from the calculator, but you can kind of see what that graph looks like when you set the window like I have. All right, then part B, we're going to determine the horizontal asymptote of the function, interpret its meaning in the context of the problem. So the horizontal asymptote is going to be at y equals 6.7. And so when you're looking at that, you can kind of trace and kind of estimate that. But that meaning would be that it's going to yield 6.7 million cubic feet per acre. Okay, so hopefully you can see, let's do this. If I go to my y equals and I put in on the next line 6.7 and I graph it, you can kind of see there's my asymptote right there. Okay, so then we go on to part C, find time necessary to obtain a yield of 1.3 million feet. So here's my equation I'm working at, and remember I want to get t by itself before I go to the calculator. So the first thing I'm going to do is get rid of this a value right here. So I'm going to divide both sides by 6.7. Now I have the exponent isolated, so I can convert it to a log. So it's going to be natural log, because that's base c, of this fraction equals the output, remember, which is the power. So it's this whole fraction right here. And then to get t by itself, I would technically multiply both sides by t and then divide both sides by natural log. And so that's what it looks like when it's isolated. And so then I can go to my calculator and I can put it in exactly like it looks here, negative 48.1 over natural log, use the fraction template, 1.3 over 6.7. So I get everything exactly as it's supposed to be. And then I'm able to come up with my value here in the calculator. And so once I've found out what t is, I can see my time here. So I would answer the question by saying it will take about 29.33 years, because we go to 3 decimal places, to yield about 1.3 million cubic feet. So remember, when you're answering an application problem, your answer needs to answer what was asked. So it was asking about the yield and how long it would take. So it told us in the original problem it wants to yield 1.3 million. So that should all be part of my final answer. It will take about 29.33 years to yield that much in cubic feet. All right, so next time we'll kind of be looking at more application problems, but this will give you a chance to brush up on your solving skills. And so I'll see you next time. Thanks, guys. Bye.